In this video, I would like to talk about quantifiers in mathematical logic. So, loosely speaking, a quantifier is like a little phrase that you see when you read a mathematical statement, like a definition or a theorem, and it indicates to you how broadly a property applies to, say, a collection that you're studying. So, it gives you a sense of the scope of the property that you're about to read a definition or theorem about. We'll see examples. And the two main quantifiers that we encounter are this one and this one. So let's go through each of them. The first one, most classically, is expressed as for all, but there are variants that you see pretty often, and they are synonymous with for all. So for each and for every. This is called the universal quantifier. The name is indicative of the scope. So it says, whatever property you're about to read about applies to everybody that you're studying, every element in the family of mathematical objects that you are studying. The notation in shorthand is this upside down capital A symbol. So you might see something like for all x in the set of rational numbers, I don't know, x squared is rational. Okay. So this means, here's a property, a statement. You could think of this as, some property of the number x. The quantifier is telling us the scope of the property. In this case, it applies to everybody in the set that we're studying. Okay, so for all x in the set of rational numbers, this property is true. The other quantifier is the existential quantifier. So the most classic expression for that is there exist. That's the writing that you would see most often. You could also see, just there is. And in shorthand, analogous to this symbol, we have this backwards capital E. Okay. So this tells you that a property is true for at least one member of the set. This doesn't mean exactly one. It's not uniqueness. It just tells us somebody has the following property. And let me give you an example kind of analogous to this. There exists a number y in the set of irrational numbers. So here y is in the set of the complement of the rational, so irrationals. And then you might say such that afterwards, such that y squared is rational. Just kind of wanted to partner that up with the first statement. Such a y could be, say, square root of 2 or square root of 3. So this is the property. And what this existential quantifier is telling us is that there is at least one member from the set we are looking at for which the property is true. It doesn't mean there is only one. And it also doesn't preclude the possibility that actually everybody has this property. But at the moment, you're just going to say there's at least one. So there exists, the existential quantifier tells you that it's true for at least one. Let me write down here, this is existential. So we have the universal quantifier, the existential quantifier, and you both want to recognize when they are being used because, again, they give you a sense of scope. You also want to learn how to bring in this shorthand notation. I like the shorthand notation when I'm writing pencil on paper. When I'm, say, typing up formal mathematics, I tend to use more of these phrases, like it's considered more proper to write out the words behind the quantifier, but both are available to you, so make sure you become comfortable with the symbolic expressions too. Let's look at some examples. Here we are looking at the definition of even and odd symmetry for functions of a real number. So for the definition of even symmetry, we say that a function f is even symmetric or has even symmetry if f of negative x equals f of x for all x in its domain. And then odd symmetry is very similar, except the condition is that f of negative x is negative f of x for all x in the domain. All right, take a moment to identify the quantifier if you haven't already done so. And then both of these are written out very formally. So perhaps it would be a good exercise to write them in shorthand. So imagine you're seeing this and you're jotting down notes. Maybe that's what you're doing right now. What would you note down in shorthand using, say, the upside down capital A symbol? Okay, the quantifier itself wasn't very mysterious because I say at the top that we're looking for the universal quantifier, and here it is. So we want to here think of this property that f of negative x equals f of x as applying to every single member x from the domain of f. So the domain of f is the collection of elements that we're looking at, and this property needs to apply to all of them. In shorthand, I might write f has even symmetry if f of negative x equals f of x for all x in the domain of f. I have ordered this a little bit differently than how I did a second ago with my statement about rational numbers. So here's the quantifier, and here is the property. So reading this, f has even symmetry if this property applies to all x in the domain of f. So the property was stated before the quantifier, but that's pretty normal. Okay, if you haven't already done so, take a moment to do the second definition. A natural thing to have written down for the second statement is almost identical to the first one. F has odd symmetry if f of negative x equals negative f of x for all x in the domain of f, and there is a certain logic to being consistent with how you phrase things. Properties might jump out at you faster if you always use the same sort of structure, but just for variety, let me write super shorthand f odd, meaning f has odd symmetry, if, I'm just going to put this first, if for all x in the domain of f, it follows that f of negative x equals negative f of x. Okay. So here I just wanted to show you examples of the universal quantifier being used in definitions. We can also look at definitions, which can be written with the existential quantifier. So here I've given almost like the childhood definitions of even and odd integers. We say that an integer is even if it is divisible by 2. And we say that an integer is odd if its remainder after division by 2 is 1. So you have 1 left over when you try to divide it by 2. Unlike the previous examples, I didn't put the existential quantifier explicitly in either of these phrases. And if you haven't seen these definitions written symbolically before, you might not be anticipating what's coming up. But if you've maybe seen these before, take a moment to go ahead and try to rewrite these a little bit more symbolically. Part of my motivation with these two definitions is actually to introduce the definitions of even and odd integers, because we work with even and odd integers a lot when we practice and build up the mechanics of proofwriting. So it's good to establish a convention for what this terminology means. Okay, let me start to write out the kind of established notion of even and odd integers. So again, here I've put like our childhood understanding of what an even integer is. I will write in the set of integers. So n is an element of the set of integers. N is even if. Okay, let's stop here for a second and see how we're going to bring in the existential quantifier. Okay, let's just take an even number. How about 18? It's divisible by 2 because 2 times 9 is 18. On the other hand, 37 is not divisible by 2 because 2 times nothing is 37. So it's like the fact that I was able to find 9, so that 9 times 2 is 18, that was what was really special there. All right, so what this means is like a number is even if you can find something whose double gives you back the number n. All right, so that's leading to the existential quantifier. So n is even if there exists a j from the set of integers such that 2j is n. Okay. So going back to my number that I picked out of 18, 18 is even because there exist 9 so that 2 times 9 is 18. So that's what this j here is referring to. And, we actually know in this case that there's only one j. So I couldn't have picked anything else other than 9, but that's not really important here. I don't need to make that precise. Just saying that there exists one is enough for this definition. All right, if you hadn't seen this before and you weren't sure how I was going to proceed with it, take a moment to pause and do something similar for odd integers. So see if you can take the second definition and rewrite it in a way which is analogous to the first. For odd integers, we can think of an odd integer as an even integer plus 1. So 11 is odd because it's 2 times 5 plus 1, and the existence of that 5 is what's really key. Okay, so m from the set of integers is odd if there exists a k from the set of integers such that m is 2k plus 1. For example, 11 is 2 times 5 plus 1. All right, this was a little bit harder to translate from these definitions to these statements with the existential quantifier, but I hope you see how this idea of finding something is coming into these definitions here. All right, let's now look at a family of statements which are going to mix together both the universal and existential quantifiers. I have here 4 statements written very symbolically. So I think the first thing we should do is go through them and translate them, maybe just out loud, into nice phrases with words. Then we will talk about negation. Save that for just a few minutes. All right, let's do the first 2 together, and then I'll pause, let you think about 3 and 4. Maybe they're harder, and then I'll come back and translate them into English as well. So the first phrase has already been written with the universal quantifier. So this is saying, for all x in the set of real numbers, x squared is greater than 0. So the square of any number is greater than 0, is basically what that's saying. So for all x, which are real, all real numbers x squared is positive. For the second statement, we have there exists an n in the set of integers such that n squared equals 2. So there's an integer whose square is 2. Okay, these might not be true, right? But they're still statements written down. Take a moment to think about 3 and 4. See if you can interpret what these are saying. Okay, statement 3 is also quite straightforward, but statement 4 deserves a little bit more work. So for statement 3, for all integers m, if m is even, then its square is even. For example, 4 squared is 16, both are even. Number 4 is a really nice example of mixing quantifiers together, and we do this a lot. All right, so let's read this carefully. Just translating the symbols out loud, it says, for all x in the set of real numbers, there exists a y in the set of real numbers such that x plus y equals 0. Okay, so I just said the symbols out loud. Logically, what this means is for any choice of real number x, at that moment, as soon as you've read this statement, for the rest of the statement, you imagine that x is fixed. So for your choice of x, there is then a y. So, let me continue the statement. Such that the sum of x and y is 0. So statement 4 is actually the existence of additive inverses for real numbers translated into a statement with quantifiers. Okay, so I really want to emphasize here, when you see these consecutive quantifiers for all x, there exists a y. What matters here is that you can choose any x you like, fix it, for that choice of x, which has now been kind of identified, even if you don't write it down, you could then go find a y to partner up with that x. So this choice of y depends on x. Okay, now what we're going to do is negate these. And, quantifiers, you can think of them just as phrases that we encounter a lot. But when we work with, say, writing proofs, we often negate statements. Maybe we're doing a proof by contrapositive or a proof of the contradiction. We will see methods that involve taking a statement and negating it. And practicing negating quantifiers helps illuminate what you need to do to show something. Okay, so let's start with this first sentence and then I'll pause. We have for all x in the set of real numbers, x squared is greater than 0. For every real number x, x squared is positive. That's actually not true, right? So if I negate it, I'm going to have a true statement. So the negation of this statement, which is false, the negation will be true. Okay, what does it mean to say that it's not the case? Maybe I'll write it out fully. It's not the case that for all x in the set of real numbers, x squared is greater than 0. So negating this statement means that it's not true that every single x makes this property true. The negation of for all x a property holds is there is an x for which the property does not hold. So that's the negation of the idea for all something is there exists an x in the set of real numbers such that the property isn't true. This property negated is x squared is less than or equal to 0. Okay, so for all x a property, to negate that is to say there exists an x such that not the property. And I picked this example because we know that this actually is false for exactly one choice of x. That x would be 0 itself. So there exists 0 such that 0 squared is less than or equal to 0. Okay, before I move on, let me say that this x here doesn't have to be unique. In this particular example, actually, there is only one x for which the property wasn't true, 0, only 0. But anytime you see the existential quantifier, keep in mind it doesn't mean that there's only one. So this could be, the negation of this statement could mean that there are few, but you just need to say that there's at least one. Okay, for the second statement, it is also false. So think about what it would look like to say that the statement is not true. So how might you start to write out like a symbolic expression saying not this example number 2. Example number 2 is also a false statement. So when we negate it, the final result should actually feel more true to us. So statement number 2 says there exists an integer n such that n squared is 2. Okay, we know that's not true. So it is not the case that there exists an n from the set of integers such that n squared is 2. There are actually 2 ways to negate this. They're equivalent, of course, but both formulations can be more useful in different contexts. All right, the first way is just to say, no, there isn't. There is no integer such that n squared is 2. So you could do that by saying there does not exist. So there does not exist n from the set of integers, and then the rest is the same, such that n squared is 2. And that feels very normal. So there's no integer whose square is 2. The other way to negate this statement, which again can be more useful in different contexts, is to say no integer has this property. There's not exist an integer with this property. In other words, all integers don't have that property. All integers have the negation of that property. So you could also say for all integers n, it is not this. Here, there's a very nice way to say not this property, not the property n squared is 2, is n squared is not 2. Okay. So if it's not the case that there exists an integer with a property, then either you can just say there does not exist an integer with that property, or for all integers, the opposite of that property. So both communicate the same negation of the original phrase. The third example, I'll let you do that for just a moment before we come back and wrap up with examples 3 and 4. Example 3 is actually a little bit tricky here. It's a preview of what it looks like to negate an implication, which is something that we will talk about in a future video. Because what this statement is saying is that for all integers m, if m is even, then m squared is even. Here we have an implication. So we have a conditional statement as the property that's following for all m in the set of integers. So let me write this as, okay, it's not going to be the case that for all, I need to write the quantifier, for all m in Z, I will write this as m even implies m squared is even. Quick remark that the original statement is true, so negating it feels a little weird, whereas here we were negating false statements and getting true statements out of it. Okay, so let's think in words what negating this statement would mean. If it's not the case that for all integers, if the integer is even, the square is even, then that must mean that there exists an even integer whose square is not even. This actually looks a lot like the first example when we said it's not the case that for all x a property holds. That meant there exists an x for which the property doesn't hold. The same thing is going to happen here. There exists an m for which this statement doesn't hold. So let me see if I can fit this on here. I'm going to start by saying there exists an m in Z such that not m even implies m squared is even. Okay, sorry about writing uphill. Again, we are going to talk a little bit more in a future video about negating P implies Q statements, but this is our first example of doing that. Not the case that the hypothesis implies the conclusion means it's possible to have the hypothesis and not the conclusion. That's what it looks like to say an if-then statement is not true. The hypothesis does not necessarily lead to the conclusion. So we can say, we continue down here, I'm just going to negate this part. There exists an m in the integer such that m is even, but m squared is not even. I think I will write and instead of but. M is even and m squared is not. Okay, I will leave this example here because we will do implications later. So to summarize, the negation of statement 3 is there exists an integer such that that integer is even and its square is not even. So we don't know how many integers would have this property, but there's at least one. And the existence of that one integer is a contradiction to our original statement. It's a challenge here because the original statement was true. So if you'd like, you could say, take this statement and rewrite it as example 3.5. For all m in the set of integers, if m is odd, then m squared is even. See if negating that feels a little better. Okay, let me pause for just a moment before example 4. This will be our last exercise in this video. For the fourth example, I think it's useful to keep in mind that this statement translated into words tells us every real number has an additive inverse. It's a true statement, so we're going to negate it to something false. But let's do this in words first, and then see if we can go symbolically and get to the same place. If it's not the case that every real number has an additive inverse, that must mean that somewhere out there is a number with no additive inverse. So again, we're going to negate a property that's true for all numbers by saying that there exists a number for which that property is not true. Okay, so at the end, what we have written down should agree with the statement, there exists a number with no additive inverse. All right, what we're going to do with this statement is just work left to right. We're going to start by negating the idea that for all real numbers x, that's the same thing that we saw here and also here. There exists, you can think of it as a counterexample. So there exists some x out there with no additive inverse. So we have to finish the sentence. Okay, so there exists an X such that not the rest of this. So the rest of this phrase here is the existence of the additive inverse. But now we are negating an existential statement that's about the existence of the Y. We did that two different ways here. Both will work. Let's do them the same order. So I'll start by just saying there's no additive inverse, cancel out the existence. So there exists an X such that there does not exist a Y, such that you can try to mix in words like so that and satisfying so that you don't just say such that all the time. But anyway, there exists an X such that there does not exist a Y such that X plus Y is 0. Okay, that does the job. But I would also like to take the other point of view. There exists an X such that there does not exist a Y, which is the additive inverse. Another perspective is for all real numbers, the real numbers are not the additive inverse of X. So negating this existence, once again, can bring us to the universal quantifier. So the other way to negate the original expression is to say there exists an X from the set of real numbers such that for all Y, Y is not the additive inverse of X. So it's like for all Y, it is not true that X plus Y is 0. The nice way to say that is X plus Y is not 0. All right, we have negated that fourth statement two different ways. One way where you just say, hey, there's a counterexample for which there's no additive inverse, like literally doesn't exist. And here you're saying, hey, there's a counterexample for which no other number, no real number can serve as the additive inverse. They're saying the same thing, but just notice the different use of quantifier there. Let me give you a moment to pause and read through these, and then I'll come back and just conclude with a few remarks. Just to wrap things up, I want to point out that we opened with 4 definitions which were written with quantifiers. Then on this slide, we had 4 examples of statements. These could be like propositions or conjectures that we're testing, which are also written with quantifiers. So you see quantifiers both in definitions and theorems. Another thing I want to point out is the more you write these kinds of statements, the more the language starts to feel natural. But notice that the universal quantifier was followed by the property immediately. So for all x in R, x squared is greater than 0. There are other ways to write that. You could say, for all x in R, we find that x squared is 0. It doesn't always have to be immediately after the the universal quantifier. Let me find other examples of that. For all integers n squared is not 2. So it was like for all, the property, for all integers m, the property, which in this particular case was an implication. And then for all x, and then immediately there exists a y such that y is the additive inverse of x. On the other hand, with the existential quantifier, you'll notice the more natural approach is to say there exists an element such that the property holds. So you'll see this, there exists and such that, there exists such that, there does not exist such that, there exists such that, and then down here too. Whereas here it was universal in the statement. I actually do not like the phrase such that used too frequently in math. I like to use satisfying and so that and kind of mix it up just because people tend to overuse such that, but that's just my opinion. Anyway, I hope that seeing the consistency in the phrasing here, though, helps you understand how to formulate these phrases on your own. We will move now into writing some proofs in the next few videos. And in some of our techniques, what we will do is perhaps look at negating conjectures or negating hypotheses or negating conclusions. And I think that this is a really good exercise. Anytime you have a hypothesis and a conclusion, you're thinking about looking at the negation of it. Always like, look at the quantifiers, make sure that you're doing it correctly. I see students make mistakes, especially with phrases like number 4 sometimes, or actually, negating propositions is often done in a way which is not quite correct, so we will talk about that specifically later. All right, thank you for your attention.